Hi friends, this is the third lecture in the lecture series for the preparation of GATE in mechanical engineering. Since this is the third lecture, please go through the previous lectures to get a better understanding. So today we will be dealing with General Heat Conduction Equation. Today we will be dealing with General Heat Conduction Equation. This and General Heat Conduction Equation is nothing but an energy balance on a body or a system through which the heat is transferred by conduction. So let's suppose a differential element in the body through which the heat transfer by conduction is occurring. So before doing that, let's define the coordinates as this is x and this is y and this is z. So let's draw the differential element. So this is the differential element through which the heat transfer occurring by conduction, and this is having dimensions dx in the x direction, and this is having dimension dz in the z direction, and this is having dimension dy in the y direction. Okay, so let's suppose some heat flux is occurring into the body in the x direction as this, and which is having value qx bar, and heat flux that is leaving in the x direction will be qx bar plus dou by dou x of qx bar into dx. Okay, so this element is having volume dv will be equal to dx into dy into dz. Okay, so this is the differential element which is having a volume dv, and some heat flux is entering in this direction as shown in the figure. So as I already mentioned, this equation is nothing but an energy balance. So let's write the energy balance equation. Energy balance, that is net rate of heat transfer plus net rate of heat generation within the body will be equal to rate of change of internal energy of the body or within the body. So this is the energy balance equation. So let's discuss each and every term in this equation. This is having three terms, and this is first, and this is second, and this is the third term. So let's discuss each and every term. So let's first go through the first term, which is the net rate of heat generation, net rate of heat transfer through this particular element. So in this we can see that along x direction a heat flux qx bar is entering, which is positive, and this qx bar into dy into dz, which will give the area, and together it will give the rate of heat transfer, and minus qx bar plus dou by dou x of qx bar into dx, which is a heat flux that is leaving this particular element, into dy into dz, which is the area through which this heat flux is occurring, which will be giving minus dou by dou x of qx bar into dx dy dz, and this dx dy dz is nothing but the dv. So we can write this as minus dou by dou x of qx bar into dv. So let's note this element as qx bar is the heat flux through the x phase, and this is the area through which the heat flux is occurring, and together or the multiplication of this will give what? Heat transfer rate. Similarly, and this will be the heat flux, and this will be the area, and together we will be getting heat transfer rate. Okay, so this is the case in along the x direction. So let's discuss similarly the case along the y direction. Along y direction we can write qy bar into the qy bar is the heat flux along the y direction, and this area will be dx into dz minus qy bar plus dou by dou y of qy bar into dy into area will be dx into dz, and this will be equal to minus dou by dou y of qy bar into dv. dx into dy into dz is nothing but dv, differential element volume. Similarly, along z direction we can write qz bar into area, which is dx into dy minus qz bar plus dou by dou z of qz bar into dz into area, which is dx into dy will be equal to minus dou by dou z of qz bar into, this is dou, this is dou into dv. So these are the rate transfer along x, along y, and along z directions. So combining all this, we can write in general that is the heat flux or the heat transfer rate that is occurring within the body along x, y, and z direction. We can write it as minus along x direction, which is the unit vector I cap dou by dou x of qx bar plus j cap into dou by dou y of qy bar plus k cap of dou by dou z of qz bar into dv. So this can be written as minus del dot q bar, and this q bar which will be equal to minus del dot k delta t. Okay, this is explained in the last lecture, so please go through it for any clarification. So in general, the net rate of heat transfer will be equal to, in general, net rate of heat transfer within the element will be equal to, we can write minus del dot minus k delta t into tv. Okay, so this is the net rate through the element. There is a minus sign over here. So next let's discuss the second term, which is nothing but the net rate of heat generation. So let's suppose q dot g is the rate of heat generation within the element per unit volume. So net rate of, therefore net rate of heat generation can be written as q dot g into dv, where dv is the volume of the particular element. So this is the net rate of heat generation. Okay, so next we will be dealing with third term, which is nothing but the rate of change of internal energy, and this will be written as dou u by dou t, where u is the internal energy, and this can be written as dou by dou t of u will be dm into c into t. Okay, where this dm is the mass of differential element and this C is the specific heat and this T is the temperature. So we can write this d dou u by dou t as dou by dou t of rho into dv into C into T, where rho is the density and this dv is the volume of the element that we considered, and C and T are the specific heat and temperature. So this can be written as dou u by dou t, which is the rate of change of internal energy, will be equal to, and this u is the capital letter U, please note that, will be equal to rho into C into dv into dou t by dou t. So rate of change of internal energy will be equal to, or can be written as, internal energy can be written as dou u by dou t will be equal to rho into C into dou t by dou t into dv. So this is the rate of change of internal energy of the system. So let's club all these three terms into one equation as first term, which is minus del dot minus k delta t into dv plus into dv plus second term, that is q dot g into dv, which is a net rate of heat generation, will be equal to this term, that is rho c dot t by dot t into dv. We can see dv in all these terms, so let's cancel all the dv's and we can write del dot k delta t k plus q dot g will be equal to rho c into dot t by dot t, and this is the general heat conduction equation. So please note, this is the most general form of heat conduction equation. Okay, so suppose if K is constant, which is thermal conductivity. Suppose a thermal conductivity is constant for a particular material. For all the engineering materials, we will be considering thermal conductivity will be constant. So we can write this above equation as del square T plus Q dot G by K will be equal to rho C by K into dot T by dot T. So this equation can be further written as del square T will be plus Qg by K equal to 1 by alpha dot T by dot T. Okay, so this particular equation is called the Fourier-Biot equation. This equation is called the Fourier-Biot equation, where this alpha is equal to thermal diffusivity. and this will be is equal to K by rho c, where K is the thermal conductivity and this rho, which is a transport property, and this rho and c are the thermophysical property of the medium. Okay, so this Fourier Biot equation will be having some special cases. So these are having some special cases. This equation is having some special cases. That first one will be for steady state heat conduction. With no heat generation or no heat generation, and this equation can be written as del square T equal to 1 by alpha dou T by dou T. Okay, so the Fourier Biot equation is reduced into this form, and this equation is called the diffusion equation. Okay, so the next special case as for unsteady state heat conduction, with internal with no heat generation, sorry, there is an error. There is some error. This is steady state heat conduction with no heat generation, and this equation can be written as del square T will be equal to sorry, there is some error in this equation, and this is having some. So this Fourier Biot equation is having this Fourier Biot equation is, so the first special case is steady state heat conduction with internal heat generation, and so this equation can be written as, so the first equation, that is this del square T, this Fourier Biot equation can be written as del square T plus Q dot G by K will be equal to 0, and this equation is called the Poisson equation, Poisson's equation. Okay, so the next special case is unsteady state heat conduction without internal heat generation, and so this equation can be written as, so the Fourier Biot equation will be changed into del square T will be is equal to 1 by alpha dou T by dou T. So this equation is called the famous diffusion equation. This equation is called the diffusion equation. So the third special case of Fourier biotic equation is steady state heat conduction, and no internal heat generation. So in this case we can write the Fourier biotic equation as del square T will be equal to 0, and this equation is called the Laplace equation. Okay, so these are the three special cases for this particular Fourier biotic equation. These are the three special cases for this particular Fourier biotic equation. And so we can see in all these equations one del square, and this del square can be converted into various coordinate systems depending upon the problems. So let's discuss this del square in various forms. This del square in Cartesian coordinate system. We can write del square will be equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. And this in the cylindrical coordinate system we can write del square will be equal to 1 by r dou by dou r into dou by dou r plus 1 by r dou by dou phi into r into dou by dou phi plus dou square by dou z square. And in the spherical coordinate system we can write del square will be equal to 1 by r square, this was r square, dou by dou r into r square dou by dou r plus 1 by r square dou by 1 by r square sin square theta into 1 by r square sin square theta into dou square by dou phi square plus 1 by r square sin square theta into dou by dou theta into sin theta dou by dou theta. Okay, so these are the various forms of del square in cylindrical Cartesian